Now we know what the phases of matter represent. We have those three phases. We have that solid, we have the liquid, and we have the gas. And we know what it takes to get into each one of those phases. What we're going to look at next is something called a phase diagram. And these are kind of complicated looking diagrams, but they're really not once you know what you're looking at, that show us all the temperatures and pressures that any of these three states of matter can exist for a single substance. But before we do that, let's make a connection. How are these two things connected? Kinetic energy and phase of matter. What do you know will connect these two? Take a moment and write that down. And the next question, what happens to the order of a substance as you add kinetic energy? As you add or you remove kinetic energy, but we'll look at the adding. So use this diagram to help you. What happens to the order, how they're arranged, how the particles are arranged as you continue to add energy? Take a moment and answer that. And what does STP stand for? And when we were looking at phase changes, we looked at things called boiling points and freezing points. And when we say the term normal, what does that mean when we refer to boiling points and freezing points? What is a substance's normal boiling point? What is its substance's normal freezing point? Because there are ways that we can change them, but what is the normal? So we're going to see two things can affect the phases of a substance. One is temperature, and remember that's the amount of kinetic energy. And the other is pressure. And they're going to have opposing effects on each other. So we're going to see something like with evaporation. We know that evaporation is vaporization at the surface of a liquid. And if you increase the temperature, you're going to increase the rate of evaporation. That makes sense. That's why we put clothes in the dryer and we don't just leave them wadded up in the sink, because they'll take a long time to dry in the sink, but if you put them in the dryer where it's warm, they're going to dry much faster. And the other one is pressure. If you have an evaporating liquid in a container and it comes to equilibrium, when you add pressure, if you were to push a plunger down, you could cause that liquid to go from evaporating back to condensing. So think about the sun, heat energy, as it strikes water, surface of water, wet pavement, again, wet laundry. The heat energy is going to cause the water to change state, and it'll go into water vapor, which will leave into the atmosphere, and an increase in evaporation. Our temperature is going to cause an increase in evaporation. So that's a direct relationship. Now, if we look at the pressure, and if we assume that the container on the right is at equilibrium, remember at any given temperature, the amount of molecules leaving the surface of the liquid is going to be offset by the amount of molecules returning. And you can affect that by increasing or decreasing the temperature. So in the second one here, we'll call B, if we increase the temperature of this system, we would see that we would have more guys filling the space above, which would cause an increase in pressure. If we decrease the temperature, we would find that we would have fewer guys hanging out in the space, and that would cause a decrease in pressure. So if we were to take this system and go to A, and we were to take that plunger and push it down, we could get to the point where we wouldn't have any evaporation. There just wouldn't be any room. You have to have this space above in order for those particles to leave. So an increase in pressure causes a decrease in evaporation. An increase in temperature causes an increase in evaporation. So that's the opposing effects. So here's a phase diagram, and again, they look horrible, but they really aren't. And what it's going to show us is the three phases of matter, the temperature and pressures that the three phases of matter can exist. And so we've looked at this: ice as a solid, water as a liquid, and water vapor. So obviously this is a phase diagram for water because it's talking about water right there. So we're going to look at pressure on the y-axis and temperature on the x-axis, and what happens to your phase of matter as you increase your temperature, what happens to your phase of matter as you increase your pressure. So phase diagrams show all of the temperatures and pressures that the phases of a sample can exist. So you should be writing this in your note-taking guide. All the temperatures and pressures that a phase of a sample can exist. And we have these two axes, temperature and pressure. So we also have these three general areas, and from one substance to another, one phase diagram to another, they all have the basic same anatomy. It's just that the shapes and the sizes of those wedges is going to differ. So that area in blue shows all the temperatures and pressures where that water can exist as a liquid. So anywhere in this little wedge here, this blue one, we can see from this temperature to this temperature, water is going to exist as a liquid. And from this pressure to this pressure up here, water can exist as a liquid. And it can't exist as a liquid outside of those parameters. Yellow area shows where water exists as a gas, and we would call it water vapor. Remember, vapor and gas, those terms are used interchangeably. They both refer to something in the gaseous state, but a vapor is a liquid at ordinary temperatures that you had to add energy to get it to go into the gaseous state. So water, we can see it. Ordinary temperatures, water exists as a liquid. We have to add kinetic energy to get it to go into the gaseous state. So water is a vapor. Hydrogen, helium, oxygen are gases. And the white shows all the temperatures and pressures where this substance can exist as a solid. So take a little quick guess here. At which point on this phase diagram would this substance exist solely as a liquid? So you have to remember which area represented which phase of matter. Generally, they're in order. So we always start here, solid, liquid, gas. So left to right, solid, liquid, gas. So which point would it exist solely as a liquid? Right here, point G. So we have these three curved lines that separate each state from each other. And you can kind of think about those lines as a fence between the 2 yards. So ice and water have a fence that separates them. Ice and water vapor have a fence, and water vapor have a fence. So this is kind of the dividing line, kind of like a border. So on this fence, any point you are on this fence means that these states are existing at equilibrium. So, for example, if you are on the fence between your yard and your neighbor's yard, so you have a block wall between your 2 yards. So here's yours, and here's theirs. And you're sitting on that block wall, and you've got your knees up, and you've got your arms crossed over your knees, so you're like a little bundle sitting on that wall. As long as you're sitting on that wall, you're in nobody's yard. You're in both yards. So you are at that border. So if you were to be pushed, whose yard would you fall in? So think about that. If you're going to be pushed, would you fall into the neighbor's yard, or would you fall into your yard? So we need one more piece of information. Can you guess what it is? And that would be, well, yeah, which direction am I going to be pushed? Well, if we push you in this direction, you're going to fall in your neighbor's yard. If we push you in the opposite direction, you're going to fall in your yard. So right here, you would be at equilibrium. You would be in both yards. And that's how we're going to look at these lines on the phase diagrams. Anywhere on one of these curved lines, you are in both yards. So anywhere on this line, ice and water are existing at equilibrium. It's freezing and melting at the same time. Water and water vapor are existing at equilibrium. It's vaporizing and condensing at the same time. So you will change your state. You can go into one or the other, but you have to be pushed. So what do you think is going to cause a push in this phase diagram? There's a couple things. We can push using a temperature by increasing or decreasing. We can push by using a pressure by increasing or decreasing. So for example, if we are sitting right here and we're freezing and we're melting, and I increase the temperature, so I'm going to push you this way. I could do that. Push you this way, you're going to end up as a liquid. If I decrease the temperature and you're sitting here, you're going to be total solid. So it depends on which way you're pushed, and we can push you temperature and pressure. Those are the things that push. So at equilibrium, remember, you are existing in both states. So anywhere on that line, you're at equilibrium. So if we were to highlight the line of equilibrium between a liquid and its vapor. So remember, we always have solid, liquid, gas. So the line of equilibrium between those two, that would be right here. So there's a couple other features on a phase diagram, and one of them is called the triple point, and the other one's called the critical point. So point C, and this is kind of interesting, shows where this substance can exist in all three states of matter, and they're all at equilibrium. So you're freezing and you're melting, and you're vaporizing and you're condensing, and you're sublimating and you're undergoing deposition, all at the same time. And that's at point C, this point right here. So that's your triple point. Now the critical point, this is something that's useful for engineers. There comes a point where once you go above that pressure or temperature, that phase of matter cannot be distinguished from each other. I think it's called a superfluid or something like that. That's where you can't tell the difference between the water and the water vapor. So they're indistinguishable from each other at that point. And that's the critical point. So we have a critical pressure and we have a critical temperature. So if we were to look at the critical pressure, we would extrapolate back from this point here, all the way back. And here's our critical pressure, critical temperature, drop down, and there's the critical temperature. So highlight the triple point in blue and the critical point in red. So triple point is easy to find because it's where 1, 2, 3, all states of matter exist simultaneously. And the critical point, remember, is at temperature and pressure, where the liquid phase and the gas phase are indistinguishable from each other. They're existing as both. It's kind of strange. Okay, here's this normal melting and points and normal boiling points, if you didn't get this at the first of the presentation. Anytime you see the word normal when we're talking about a phase change, this normal, that means at STP, standard temperature and pressure. Actually, with this one, it's going to be the standard pressure. So we said standard pressure for STP was 1 atmosphere. It could be 101.3 kPa, or it could be 760 millimeters of mercury. All of these are equivalent. It's just different units describing the same thing. It's like 1 foot is 12 inches, etc. So when we talk about normal, we are looking for what happens here at 1 atmosphere. There's our normal pressure. So we know that a substance's freezing point and melting point occur at the same temperature. So if we wanted to find the normal melting point of ice or of water, we would go from this one and continue on until we hit that line of equilibrium. Now this is the melting point and the freezing point. And then you drop down to find the temperature. So we know that water freezes and melts at 0 degrees Celsius. If we wanted to do the same thing for the boiling point, we know that water will boil when atmospheric pressure is equal to the vapor pressure. So all along here is our vapor pressure. So here's our normal atmospheric pressure. Drag it all the way over. And as soon as we hit that vapor pressure line, that's when we get to boil. Drop down. What temperature is that for water? It's 100 degrees. So normal refers to a substance at STP, standard temperature pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. But when we're talking about boiling and melting points, we're looking mostly at that pressure. So highlight the dotted line at normal atmospheric pressure. So that would be, remember normal is this one. And whenever that line crosses a line of equilibrium, that change of state is going to occur. So for example, let's start here. Here we are all solid, and we stay solid at all these temperatures and pressures until we hit that line of equilibrium. Now we are starting to melt or freeze, depending on which way we're going, but we're going to go from left to right. Now we're liquid. So always liquid, nothing but liquid, and we can continue to be a liquid until we hit this line of equilibrium. Now we're vaporizing. Now beyond that, it's all vapor. So try this, answer in your notes, what happens to a liquid when its vapor pressure equals atmospheric pressure? So remember, we said your vapor pressure is anywhere along this line between a liquid and its vapor, and here's your atmospheric pressure. So what happens when vapor pressure meets atmospheric pressure? What temperature does it happen for water? So where does your atmospheric pressure equal your vapor pressure? Hit the line. It says what temperature, so we need to drop down. And there's our temperature. So look at this diagram and see what happens to the boiling point of water if we increase our atmospheric pressure. So let's look at that. So remember when we talked about the things that can affect the phases, we said temperature was one, or kinetic energy, and the other was pressure, and they had opposite effects. So an increase in temperature is going to cause something to go from a solid to a liquid. An increase in pressure is going to cause something to go from a liquid back down to the solid. So let's look at what happens with those pressures, or what happens to our boiling point. All right, so let's say we are in Death Valley, so our pressure is increased. So Death Valley is the only place on the surface of the earth that's below sea level. So it's a little bit above 1 atmosphere. And so let's see what happens as our new, which is not the normal, our new pressure hits that vapor pressure line. So remember, anytime it crosses that line of equilibrium, that's what happens. Okay, so here we're hitting the vapor pressure line, which means our vapor pressure is equal to new atmospheric pressure, which means we get to boil. So what's happening to the boiling point? Normal was here. With the new pressure, higher pressure, it's right there. So what happened? So some of you may know what this is. It's a pressure cooker. And a pressure cooker has a well, it's used to cook foods faster. What it has is it has a seal on the lid. So normally if you have just a regular pot on the stove and you have a lid on it, it starts to boil. You see that lid bumping up and down because the vapor is pushing against it. Well, with this one, it can't because it is sealed, and then it also is kind of locked into place. So when we talked about heating a sealed container and how that was a bad idea, because you know you've got those particles of gas, and as you increase the kinetic energy, you increase their motion, which increases the pressure. And so if you increase that pressure enough, this thing's going to blow. So this pressure cooker allows you to heat a sealed container. And so here's our pressure gauge here. I think this is kind of an old-fashioned one. They have more modern ones now. But as we have a liquid in here, and as it starts to reach its normal boiling point, remember, atmospheric pressure has to equal vapor pressure. So as this is heating and it's starting to evaporate, we're starting to create a vapor pressure. Now, since this vapor pressure, these particles aren't allowed to evaporate, we're able to increase the number of particles above that liquid. So if we're increasing the number of particles above that liquid, that means we're increasing the number of collisions, which means we're causing an increase in pressure. So back to your phase diagrams. If this is under higher pressure than normal, what's going to happen to your boiling point? Let's go back and see. So we've created, with that pressure cooker, an artificial environment that has a higher pressure. So what happens to your normal boiling point? It increases. So that means the water is hotter than 100 degrees Celsius. So that's how your food gets cooked faster, because you're cooking with hotter water. So what temperature on this phase diagram does water begin to freeze? So we're looking at the normal freezing point. So remember, normal means 1 atmosphere. So normal freezing point, we're going to go take this pressure, and as soon as we hit that line of equilibrium, that phase change is happening. So right now we're melting and we're freezing. So freezing point, melting point is at the same temperature. So we drop back down and we look at that temperature. Now, here's an interesting one. I live up in Running Springs, so I live at a high elevation, 6,000 feet. And so generally, if it's raining down at sea level, it's snowing up where I live. And why does water rarely freeze at sea level? So if we talk about sea level, it has a higher pressure. So remember, as we increase our pressure, we go, let me start from our normal freezing point. If we were to increase our pressure, we would go from a solid to a liquid. So if you're at a higher pressure, even though you're at 0 degrees Celsius, you're not going to freeze. So under normal atmospheric conditions, again, normal means 1 atmosphere, and this case, atmospheric conditions, about 35 degrees Celsius. What's the most common phase of water? So you're going to have to take your lines. We said normal pressure and 35 degrees Celsius. Here's 50-ish, right in the middle, but between 0 and 100. So 35 would probably be around there. So draw your lines and find the normal or the most common phase of water at these atmospheric conditions. So what's going to happen to our boiling point of water as the atmospheric pressure is decreasing, as the pressure is getting lower? Okay, well, let's look at that. So here with our pressure is increasing. Here's our 1, our normal, and pressure is decreasing. So let's decrease our pressure and think about how could you decrease your pressure. Remember, if we talk about sea level to high elevations, that if you're at sea level, you have a much larger column of air above you, so this would be high pressure, And if you're at higher elevations, the column of air above you is much lower, so this would be low pressure. So that means we have to decrease our pressure, and let's take it a little bit below the 1. Now, let's look at what happens to our boiling point. So remember, when your pressure line hits any line of equilibrium, that phase change is happening. There, now we've hit our vapor pressure line. So as we drop down to see what happens to the temperature, what do you notice? What happens to the temperature, the boiling point, if your atmospheric pressure decreases? And I think I'd mentioned this to you before, going up in really, really high elevations. This is Mount Everest. And let's say you were on one of those expeditions to go up to Mount Everest. Why anybody would want to do that, I have no clue. But you go up there and the atmosphere is so thin that you have to take canisters of oxygen to breathe because there's not a lot of air up there. And so if you decide you're going to go up there and you want to make camp, say we're going to make camp somewhere around in here, and you decide, well, I'm going to make some egg salad, so I need to hard boil these eggs. Why you're carrying eggs, we won't worry about. So I got these eggs, and I get my pan out, and I put the water in there, and I start to heat it up. And I'm heating the water, and all of a sudden it starts to boil. I'm like, yay, here we're boiling this water. And I put the eggs in there, and I'm like, 7 minutes is a perfect time to hard boil these eggs. And after 7 minutes, I take the egg out of the water and open it up, and it's raw. It did not cook. So what happened? Let's go back to the diagram. When we decreased our atmospheric pressure, we also decreased our boiling temperature. So instead of boiling at 100 degrees, the water's boiling at 70 degrees or lower. You can put your hands in there and it's not going to hurt you because the temperature is too low. But our vapor pressure at that point reached atmospheric pressure, and the rule is when that happens, you boil. Doesn't matter what the temperature is. Vapor pressure equals atmospheric pressure. Anywhere along this line, you're going to start to boil. So what are the variables plotted on this diagram? What are the things that can change? Oftentimes people get confused and they think we're talking about the solids, the liquids, and the gases. No, that's not it. You think about in science variables or in a graph. What are the variables? Well, you have the dependent and you have the independent variable. So the dependent variable is always on the x-axis. So that's our atmosphere. I'm sorry, y. And our independent variable is the x, and in this case it's temperature. So our variables are atmosphere and temperature, or pressure and temperature. So what phase of water is represented by area 1? I'll let you do that. And 2 and 3. And what does line A represent? So we're looking at this one here. What does that represent? And what can be done to increase the boiling point of water? Give an example. And how would you decrease the boiling point of water? Give an example. And using at least 5 sentences, summarize what you just learned. And let me know if there's anything that you didn't know before that you found particularly interesting.